Let's look a bit more closely at what alpha, beta, and gamma decay really are. What's happening in the nucleus during these processes. So we're going to talk about nuclear decay and conservation laws, because like the conservation laws you might have learned about last semester and still remember, conservation of energy, conservation of momentum, etc., there are conservation laws when dealing with nuclear reactions. They're similar to the conservation laws dealing with chemical reactions. If you've had a chemistry class, you probably balanced equations, right? Made sure you had the right number of oxygen or hydrogen on both sides. Make sure you have the same number of electrons on both sides, and so on. So an unstable nucleon will decay, and that decay goes from a parent nucleon into one or more daughter nucleons. So just basically, a nucleon can split. There's also a way of decaying without actually changing the properties of the nucleus, except for the energy. We'll talk about gamma decay in a bit. But a nucleon can split from a parent into a daughter. These decays continue until the nucleon transforms into something stable. Once it's something stable, it doesn't want to decay anymore. But that can take many, many, many steps to go from a highly radioactive material into a stable material. For example, uranium decaying into lead. Lead would be the stable final product. There are many steps and many different paths uranium can take to decay into lead. And so a little diagram here showing uranium all the way down to lead. There are many, many different steps and paths that a nucleon can take. All right, so the first step is called alpha decay. It's one of the possible steps it can take. Alpha decay, again, using the Greek letter alpha, is when a nucleon, again, using the general rule, the mass number, the atomic number, chemical symbol, or the element symbol, and the number of neutrons, when effectively, think of it as a massive nucleus that spits out a helium atom. The helium atom is the alpha particle. It has high mass, right? There's 4 nucleons in there, 2 protons and 2 neutrons. So 8,000 times approximately the mass of an electron. So its high mass is highly charged. This is not a neutral helium atom. It has no electrons attached to it. So it's ionized. It has a charge of plus 2e. It's massive and it's weakly penetrating. It's a huge boulder traveling very slowly that's easily stopped by, again, just a sheet of paper. But to spit out a helium nucleus, to spit out an alpha particle, you have to take the nucleons from somewhere. And in this case, the nucleons come from the original nucleus. So the atomic mass, the mass number, right, drops by 4 because 2 protons and 2 neutrons are leaving. The atomic number drops by 2. And since the atomic number is changing, the number of protons in the nucleus is decreasing, which means the element changes. It's not this element anymore. It's a different element because it has a different number of protons. So an example of this, plutonium-239. Plutonium has 94 protons. That's what makes it plutonium. 239 total nucleons. And if you want the neutron number, which I don't have, you just subtract these 2 numbers. So it would be 143. Oh, sorry, 145. Spitting out a helium nucleus, the number of total nucleons in the nucleus drops by 4. So plutonium-239 becomes 235. The number of protons drops by 2. 94 protons becomes 92 protons. An element with 92 protons in it is uranium. So plutonium-239 decays into uranium-235 plus an alpha particle. Conservation laws. Atomic mass has to be conserved. The mass has to go somewhere. Well, yes and no. The number of nucleons has to be conserved, but what happens is a little bit of energy is lost because a little bit of mass is lost. If you actually calculate the total mass of plutonium-239 and compare it to the combined mass of uranium-235 and a helium nucleus, helium-4, you'll find that plutonium weighs a tiny bit more than these two put together. Where does that missing mass go? It's released as energy. That missing mass goes into the kinetic energy of the helium nucleus. If we want to think about it that way, the helium nucleus spits off, and of course, conservation of momentum, uranium is recoiled because of that. So they both have a little bit of kinetic energy flying off into space. That can heat the surroundings. Shoot a little alpha particle bullet out of a plutonium nucleus. That little alpha particle will hit something and transfer energy, transferring kinetic energy, heating an object up. So the energy is lost via kinetic energy. So this is probably the easiest one to deal with as far as conservation rules, right? Charge is conserved. You have plus 94 protons here, 92 plus 92 protons here, 2 protons here, so a total of positive charge of 94 protons. I'm not worried about electrons. This is a nuclear reaction, right? Electrons can come from the nucleus or can be absorbed by the nucleus, and we'll talk about that in the next part of this video. But for alpha decay, we're just worried about the same number of particles before and after, the same amount of positive charge before and after. That is alpha decay. Now let's look at the next two major types of reactions. Both are called beta decays. In fact, there are three here. Beta decays. Beta, again, the Greek letter beta, looks like a bee with a long tail. In beta decay, there are two major types of beta decay. There's beta minus decay and beta plus decay. So let's look at the first one first. Beta minus decay. It's when you have parent nucleus that spits out an electron, and when it spits out an electron, what ends up happening is the mass number doesn't change, A doesn't change, because remember electrons are tiny compared to the mass of the nucleons. So there's the same number of nucleons in the daughter nucleus here, but conservation of charge says that if we started off with Z positive charges on the left side, we have to have Z positive charges on the right. Well, here we have Z plus 1. So the only way we can get Z is if we add a negative charge to it, right? Z plus 1 and adding a negative 1 takes away that additional 1 here. So when you add up the total positive charge on the right-hand side, you see that's equal to the same as the left-hand side, Z, whatever that number was, whatever the atomic number is. So the nucleus effectively spits out an electron. That changes the element because the element now has a different number of positive charges. So effectively what's going on in the nucleus here is a neutron is becoming a proton. So the neutron number drops by 1, the proton number increases by 1. So in the nucleus itself, a neutron spits out an electron and becomes a proton. And since it becomes a proton, it gains charge. Now you're like, oh, additional proton here, that electron must go into orbit around the atom then. No, far too much kinetic energy for the most part. The electron is shot out like a little bullet. Low mass compared to an alpha particle, it's 1/8000th approximately, assuming that electrons are 1/2000th the mass of a nucleon. That's actually close to 1800. There are 4 nucleons in an alpha particle. There are no nucleons in a beta particle, it's just the electron. So much, much less massive. So it actually can get much higher kinetic energy, because remember kinetic energy is 1/2 mv squared, so much less mass means V can be greater if you kick it out with the same energy. Weakly, moderately charged compared to helium. Remember helium, the alpha particle was a +2e, this is -1e charge. And then this weird particle over here. Another conservation law in nuclear reactions we'll learn is conservation of lepton number. Electrons are called leptons. It's a type of particle. There are 3 major types of leptons. There's the electron, there's the muon, and the tau. You've probably not heard of any of the other types. Each of them has a corresponding neutrino, which you might have heard about. A neutrino is a very, very low mass particle. For a while, it was even thought to have 0 mass, but we've now actually measured the mass of the neutrino. It makes the electron look massive. Neutrinos are very weakly interacting. So weakly interacting, and they're very difficult to detect. They're so weakly interacting that in the size of your thumbnail, every second, about 1 trillion neutrinos go through. but in your lifetime, your body will only be hit by a few. They can fly through light years of lead and not interact. The bar on top of this means it's an antineutrino. That means it's antimatter. So conservation of lepton number means that you have to have the same lepton number on both sides of a reaction. Regular matter has a lepton number of 1. Antimatter has a lepton number of -1. So there are no leptons on the left-hand side, no electrons, no neutrinos. So the lepton number is 0. On the right-hand side, this is not a lepton, the new element. This is a lepton. An electron has a lepton number of +1. An anti-electron neutrino has a lepton number of -1. +1 plus -1 is 0, so the lepton number on the right-hand side is 0. So this reaction balances. An example, cobalt-60 can decay into nickel-60. Again, the number of nucleons doesn't change, so the mass number stays the same. A neutron becomes a proton, though, so the neutron number drops from 33 to 32, while the proton number goes from 27 to 28. Because a neutron becomes a proton, it spits out an electron and an antimatter neutrino that goes flying off. That is beta minus decay. Beta plus decay is the exact opposite in terms of charge. Instead of a neutron becoming a proton becomes a neutron. So the proton number, or the atomic number, drops by 1. The neutron number increases by 1. But remember, charges have to balance. So this has Z positive charges on the left. This must have Z positive charges on the right. It has Z minus 1, so it has to have another positive charge somewhere. That comes from this object called a positron. This is antimatter. It's an antimatter neutrino. Sorry, an antimatter electron, not a neutrino. Neutrino comes next. This is an antimatter electron. It has the exact same properties of electrons except charge. It has a positive charge, +1e, versus an electron which has a charge of -1e. So we're introducing the concept of antimatter now in nuclear reactions, which is a rather fascinating phenomenon. Not much antimatter in the world at all. It doesn't survive. There's actually, our universe is made out of matter and not antimatter, but antimatter particles do appear. Now remember, antimatter has a lepton number of -1, so this has to be balanced with a lepton of a number +1, which is an electron neutrino. Notice there's no bar above here. If there's a bar above it, it means it's an antimatter neutrino. If there's no bar, it means it's a regular matter neutrino. So this is beta plus decay. And then finally, nuclei don't just spit out electrons. Sometimes a nucleus can absorb an electron. A free electron's flying in space, interacts with the nucleus sucks it up, and what ends up happening then is a proton becomes a neutron. So apologies, I'm missing a little bit here. There should be n+1 here. The neutron number increases, proton number decreases, changing the element. Remember, conservation's law says that charge must be conserved. You have a charge of Z here. Electron has a charge of -1, so this ends up having a total charge of Z -1 on the left-hand side. You have a charge of Z -1 on the right-hand side. Neutrinos have no charge. Neutrino means little neutral one, basically. So charges are the same on both sides. The nucleon number, A and A. Nucleon number is the same on both sides. Lepton number. This is an electron, which has a lepton number of +1. This is a matter neutrino, an electron neutrino, which has a lepton number of +1. So there's +1 leptons on both sides. That balances. So this is electron capture. So beta particles deal with electrons. Specifically, again, the emission of a beta particle is the emission of an electron or the emission of a positron. For beta minus decay and beta plus decay, respectively. And finally, we come to gamma decay. Now, gamma decay is unique amongst radioactive decay because it actually doesn't change the parent and daughter nuclei in terms of what element is there. So what ends up happening for gamma decay is you have an excited nucleus. The little star there means it's excited. It has additional energy. Think of, in an atom form, an electron that's at a high orbital. And when that electron falls down to a lower orbital, it emits a photon. The same thing happens here. The protons and neutrons are in an excited state. They fall to a lower energy state and emit one or more gamma rays, usually more than one gamma ray for conservation of momentum. So these gamma rays that are emitted basically take this energy away. It's the same principle as when an atom with a high electron energy state falls back down. It's just that energies in the nucleus, because of the nuclear strong force, are millions of times greater. So the energy of the photons can be millions of times greater than the energy from electron transitions. Like for the hydrogen atom, the n equals 3 to the n equals 2 energy transition for a hydrogen atom has a wavelength of around 656.3 nanometers. Gamma rays can be significantly more energetic. Now, it's a photon. It's a high energy photon. We talked about gamma rays when we talked about light. Gamma rays have zero charge because it's a photon. Photons don't have charge. It has zero mass because it's a photon and photons don't have mass. So it is very highly penetrating. So gamma rays can penetrate much more easily through materials. Just like X-rays pass through your body, gamma rays are even more energetic and more easily pass through your body, or pass through materials. So the element doesn't change, right? Number of protons stays the same. Again, looking at conservation, number of nucleons is the same on both sides. Number of protons is the same on both sides. So the charge is the same on both sides. So this keeps with our conservation laws.